So she doesn't have the exam one key up yet. So in case someone wasn't there, so to avoid an unfair advantage in terms of the exam, I'm not going to go over it until she has the key up. So we're mostly going to do free body diagrams with these two. I did want to just walk through some of these because I did these three problems on supplemental number 7. Sorry. But I was made aware that Zoom was not recording the video. So I greatly apologize for that. Anyway, just a quick walkthrough. Here it says the plane is traveling this direction. This is just finding the two components. So you would find the x. Sorry. To find the x and y components, right? Probably do with the y first and then the x. She would probably have you like find this entire angle. I just like to use the angle given and then know that this is a negative x and a positive y. From there, you would calculate those. Remember, it's going to be sine in this case because it's on the opposite side. Sine. This one's adjacent to the angle, so it's going to be cosine. And ask how far north and how far west the plane has traveled after so many hours. So that is just your velocity in a direction times the time passed. And the reason for that is right because you have velocity is equal to delta x over delta t, where your t naught is equal to 0, so it's basically just t there. And then that's actually going to be x component. Nothing too hard. And then the next one is an ant walking along an axis. This one's a bit more complicated just because you have to draw the vectors yourself. But this is a tail to tip method in particular. So that means if it says it walks so much in straight along the x-axis, so it's going to be like that. I'm just going to rush through these real quick. And it turns left 30 degrees. Remember, that's left from the nth perspective. So then it's going to be left 30 degrees here, where it's 30 degrees from where it was. And then turns another 70 degrees to the left. Right, that's your angle now. So then using these, you would find the x and y components for each one. All right. Yeah, that should be fine. I probably just drew the angle weird. Or more like this. Yeah. Sounds a little hard to imagine. This one's all x. And then you would add up all the different X and Y components, and that will get you that answer. Then this one's just a projectile motion. We've already gone over quite a few of these, so it's the same idea where have your V naught against V star, your V naught have Vx and Vy. And then you'd like find it based on your angle. This one's gonna be sine, that one's gonna be cosine, et cetera, et cetera. Then you plug those into your kinematics equations to find your times and stuff, and that's how you do that. Now, of course, if you guys ever have any questions or solving these, you're always free to chat me or text. And then back to the ones that we were gonna do today. So I was gonna just do a basic free body diagram, these two basketball players, because I remember her doing it for us. Right, this basketball player has normal force on him. You could probably draw the normal force from here, pushing up on the ground, then his gravity pulling down. So for this player, we have force normal, then force gravity. Then you have Fn, and that should be the same as Fd because he's not moving. So there's no forces acting on him and it's an equilibrium. Whenever you see equilibrium, that means that all the forces sum to zero. In the y direction. And then there's no forces in the x direction either, so you're good there. And then for the guy up here, right, we have force gravity here. Then you don't have anything pushing up because he's not touching the ground. So it would just be the force gravity vector. That's all you draw. So you could do, if she asked for why isn't he like falling, you would say something like he is falling, but his initial velocity was heading upward. So his velocity needs to come to zero before he starts falling. So then his total acceleration in the y direction is going to be his mass times the acceleration, probably gravity. So his total acceleration is gravity. Remember that acceleration is different from gravity. Sorry, acceleration is different from velocity. You can have a positive or negative acceleration and have a velocity of an opposite sign. Because acceleration is just telling you which way you're going depending on your axis of your defined axis. Okay. This one's a little more difficult. Which you have two boxes and you have someone pulling on them. So the way first you need to draw all your free body diagrams, right? They have normal force A, big A. You also have your normal force of B over here. Let me see if I can change the color. Ah, I don't really read it, so we're not going to. And you have force of gravity on B. Note that both of these vectors should be about the same length. It's just kind of hard to draw. Also, she's not gonna like drop points if they're slightly off, like a few centimeters off. But if they're noticeably different sizes, she might drop points because you have to understand that at least in this direction they're in equilibrium. And then one last thing, we have a rope here in the middle, so that means there's force tension along that rope. And that's kind of like normal force, whereas it depends on the other forces acting on the body. So on this body, force tension is pulling it this way, and this body is pulling it this way. But they're both equal to each other. So I guess we can label this one, see if I can wrong. I'll just put B here and A over here. Where no, because you're gonna draw the negative positive depending on the relative area. So we can go ahead and get into our equation. I'm gonna type down for these because I feel like it's faster that way. Have F of Y is equal to force. Oh, let's do B. FYB force NB minus force DB equals to 0 Newton. Is there an equilibrium? Similarly, FYA equals to FNA minus FEA with 0 newtons. And then you're basically not going to touch that because it doesn't say friction. If you had friction, then you would need these normal forces to calculate how much friction is acting on the boxes. But for now, you don't need that because I don't think there's probably friction. Then you also have XP. Is equal to boundary is force tension. I guess I should probably put parentheses in. Okay. This one's gonna have force pull minus the force tension. I'll leave it as T. It just looks weird. And you don't know if you have a zero acceleration or not. So you're still gonna do it in and these are relative to the box that you're holding. And I note that the boxes are connected, so the acceleration of A is the same as the acceleration of B. And I'll rewrite that. These are supposed to be in subscripts. You know, the subscripts tell you which one you're like using. So acceleration of A, same as acceleration of B. Like this one's MB down here. Acceleration of B. That's how that looks if you were to actually write it. Okay. So then which ones are we going to use? Well, we don't know force tension and we don't know acceleration. But we know everything else. So we probably rewrite these by plugging this into there. And we'll do all this is equal to A. And plug those into for acceleration. Which means force push minus, and I'll just leave a space for the B, A, equals M. I'm gonna leave a space for the A. So, right. So basically it's saying the force of your push is equal to the mass of B acceleration minus the equals the mass of A times acceleration. So then that can be rewritten as force push equal to M A acceleration. I'm going to leave a space. Plus M B acceleration, which is the same as acceleration times M of A and M of B. And I'll just go ahead and write in the subscripts. Right, and we get that acceleration out because we factored it out. So then that becomes, I'm just gonna write this in force push. Oh, let me show my logic on this. And a factor And then you can divide all of this. Then over here, you took all of this and moved it over. And the reason you're doing all of that is to isolate it. Okay. Maybe now we can get back to the girl. Over. Force. And it gives you your force push, which is 40 newtons. And it gives you your I'm gonna just type it. And then some plus 12 kilograms. I'm getting these numbers just from the photo. And then if you plug that in, it should be 1.8 meters per second squared. I'm gonna just write that in. Right? Because you know that Newton kilograms times meters per second squared. And then if you divide that by kilograms, those cancel out, and you get meters per second squared. Cool. That's just making sure that your units make sense. Anyway, from there, we still need to find force T. So, we solve that. I'll put the answers in a different color. And then for tension, probably the easiest one would just be use Ft is equal to mv. So we're gonna take that, bring it all the way over here. I'm gonna type it. Times acceleration, which is 12 kilograms. times 1.8 meters over seconds. I'll leave the space for the square and write it in. Once you plug that in, it should be 21.6. First tension. Oh, oh. So I don't even put that in. Tension. And again, because Newton is equal to kilograms per meter per second squared. Okay. Um, I'm kind of have something to do at like 1 and no one has shown up, so I think I'm gonna end the meeting.